This is problem 5-30. It's on page 303, or at least the figure is. Let me sketch it. So here's the beam. We've got a reaction load at either end and a distributed load along the length of the beam that looks something like this. Now the distributed load is constant at 150 newtons per meter, at least the first one is. The next one is 500 newtons per meter, and all that means is for each meter you've got 150 newtons, and over in this section for each meter there's 500 newtons applied. And the dimensions are pretty nice. They're a half meter for each section. Okay, let's start off with the loads, or basically the reactions, and see what we've got. Now, do you guys remember how to deal with distributed loads? The easiest way, regardless of whether they're a rectangle or a triangle, is to just find the centroid and apply the effective force there. That's the easiest way. So let me switch colors. And what I'm going to do is say, well, we've got a half meter's worth of 150 newtons per meter. So how many newtons is this total load? Half of that, right? So it's 75. So essentially, there are 75 newtons applied here. Now, we can't do this once we start talking about shear. We have to do something a little different. But for the sake of calculating the reactions, this will work fine. Now, what's the resultant load, I think is what you would call it in statics. What's the resultant load of this 500 newtons per meter acting over a half meter? 250. Now I can go and approach this as a regular statics problem, where this is A, this is B, and just sum moments again about A. Okay, so summing moments about A, I'd have 1/4 meter multiplied by 75 newtons. Okay. Now I'm dropping the units because when you get really fast with this, when you're used to it, you don't have to worry about it so much. As long as you're consistent with your units, it'll work out. But in most of my classes, and most of the time in this class, I drill you on units pretty hard. So just make sure you know how to use them. Okay? But I get tired of writing N's and M's when they all are the same. Okay, so there's the distributed load resultant. We need this one, which is going to act out at 3/4 of a meter, right? So plus, oh, wait a second. That should be minus, because this is a negative moment. So it's acting down, it's going to cause a negative moment. I've chosen the opposite direction as positive. I've chosen counterclockwise as positive. Okay, so let's take care of this one. Distance, 3/4 of a meter, 250 Newton load. And then finally, the length of the beam is 1.5 meters, and the reaction at B is the unknown we're looking for. So now let's calculate the reaction at B. Let's see, what I'm going to do is just add these two together and divide by 1.5. So 1/4 of 75, I could have done that in my head, that's 25. And 3/4 of 250 divided by 1.5. I got a reaction at B of 137.5. Anyone do that with me and get the same thing? Yeah. All right, good. So then now let's sum moments at B. Okay, summing moments at B over here, we'd have a positive, let's see, this is going to be 3/4 multiplied by 250, plus the distance from here to here would be 1.25 of a meter multiplied by 75. And then the reaction at A is going to be a negative moment, so that would be 1.5 times the reaction at A. So now solving for the reaction at A, let's see, 3/4 of 250 and 1.25 of 75. Quantity divided by 1.5 gives me 187.5 for the reaction at B. We add 137.5, we get 325. 75 and 250 are 325, so life is good. It seems to work. Okay? I think we've got the right values of our reaction loads. Okay? Can I erase this? Now let's go for the shear. Let's see, I don't want that to be quite so long. I need room for the moment. The shear will be measured in newtons. And think with me, if you were to cut the beam just to the right of this load, the distributed load has had no distance to add up, right? And so the shear would have to be 187.5 down like that. So we begin our shear diagram at 187.5. But as we move along, what happens is the distributed load keeps resisting this 187.5, right? It keeps helping us keep this beam in equilibrium as we add more and more beam, and therefore more and more of the distributed load. In fact, by the time we get to this point, the distributed load is applying 75 newtons against that 187.5. So the shear has to go down. So in other words, if we were to cut the beam here, we still need shear in this direction, but we would take 75 from the 187.5, and that's the value of the shear just to the right, not into this other distributed load yet. Now let's see, if I do that math in my head, I might make a mistake. I think it's 122.5, but I'm not sure. I may not be thinking right. Minus 75, no, 112.5. Good thing I used the calculator. Now, the way the shear decreases between these 2 points is just linear, right? Because the distributed load adds the same, or takes away the same amount of shear for each millimeter that you move along. So this will come down, but it won't come to 0. In fact, this value, as I said, is 112.5. It's just the difference between these two loads. Okay? Now, as we move into this distributed load section, in other words, as we add more and more of the beam, or we cut the beam farther into the farther to the right, the second distributed load is going to help resist this 187.5 Newton force. In fact, it would cross at some point. Now we should figure out where that crossing occurs. Okay, and we'll do that in just a moment. But let's figure out, first of all, where we'll end up. We've got 250 newtons, which if we subtract that from the 112.5, means we end up below the axis at this section of the beam, down at 137.5. So let's see, I'll try to do this the best I can. So something like this. Okay, so this is negative 137.5, and that's a good thing, because what ends up happening later is we've got a 137.5 Newton load to take the shear back. Now, does the shear change from this point to that point? Well, no. The amount, imagine cutting the beam over here, the amount of reaction we need in the beam, the amount of shear, in other words, would be the same until we finally get out to where that takes care of it. So this would just move across and come up like this. So we've got the shape of this correct. We've got all the magnitudes labeled, but we should find this crossing, right? That's something we should do. So how would we do that? Well, we know that every meter we move along gives us another 500 newtons. How much do we need? Well, we only need 112.5 to come to 0. Okay, so how far do we need to go in order to get 112.5? Well, the way to do that is just take the 500 and divide it by 112, right? Or the other way around. It would be the 112 divided by 500. So 112.5 divided by 500. We only need to go 0.225 meters in order to get to that point. Does everybody see how I got that? Any questions on it? Did I get it right? I think I got it right. So as we add more and more load, and we can check it, but if this is a half, then this distance here should be 0.225. To check it, what I'll do is I'll multiply this distance, 0.225, by 500, and sure enough, I get 112.5. So that worked out. Okay? Now how about the moment diagram? The moment diagram is a little more difficult conceptually, because now we're going to have curves that are not straight. Okay? The moment is still just the integral of the shear diagram. So in other words, the moment's going to begin at 0, and that makes sense, because again, considering a cut on the beam, Yes, we'll have shear, but there's not much distance, and so there's no moment as we're close to the left-hand load. Okay. As we add up area, notice that initially we're adding area very quickly, right? And so would this be concave up or concave down? How many people want to vote for concave up? How many people want to vote for concave down? I agree with down because look, we add a lot of area. You go a short distance, a lot of area is added. That's a big change in the moment. As you go along farther and farther, you add less and less area, so it's less drastic. Does that make sense? Okay, so it is concave up. Now exactly what does the shape of that look like? It doesn't matter. Right? It doesn't matter too much. We just need to know that it's concave up. So there we go. What's the magnitude of that moment? Well, now we've got to calculate this area, and it's not quite as easy as it was before. The way I do this is I just look at it as areas. So there's a rectangle and a triangle. I need both areas. And the easy way to do this is to calculate a rectangular area for that upper triangle and divide by 2, and then add the lower rectangle. Okay? It's quick and easy. So what is this? Well, the difference between 187.5 and 112.5 is the height of the triangle times a half times a half. So the upper triangle is 18.75 Newton meters of moment. Okay, and now we need to multiply half by 112.5 to get the lower rectangle. 12.5 times a half. There we go. So it's 75. So the value of the moment. I tell you what, let me just write it over here, is 75 Newton meters. Now it's not easy to draw the next part. We're still adding to the moment, right? Because there's still more area being added, more moment of the shear being added. So should this curve continue concave up or concave down? Same argument as before. As we go along, we're adding less and less. So it's still concave up. Now, I can't draw this well because I'm not a graphing calculator. But if I were to draw this, I would continue with concave up, but it shouldn't do something like this. Does that make sense? Because look, we're adding less and less area than we were even before. So this should continue upward, but I should have ended it still with an upward slope. That way I could come off of it with an upward slope, but not as great an upward slope. Again, my diagram's not going to be very pretty by comparison to what a computer could generate because it would actually plot all of these points. Okay? So this should not be any higher slope than any part of this lower curve. Okay? How far does it go? Well, all I got to do is add up this area. That's 0.225 multiplied by 112.5 divided by 2. So plus 112.5 times 0.225 over 2. Okay, so this comes out to 87.66 or so. There's 5 decimal places on my calculator. I don't really want them all. Okay. Now, how about the next section? Well, now we're going to subtract area, right? So the moment's going to have to go down. So this is a maximum, right? This point is where the moment maxes out. So now we're going to decrease the moment by how much? Well, basically just this triangular area here. Okay. But would we, again, would we be concave down or concave up coming away from this? What do you think? Concave down, right, because think about it. We're not going to change much initially, right? So it's going to pretty much stay the same. As you get farther and farther, it's going to change more drastically. Okay, so it would be concave down. Now, how far down do we go? I don't know. Let's figure it out. This is 137.5. This distance is going to be whatever's left over from that half meter after we remove 0.225 meters of it. Okay, if we do that in our heads, that should be 0.275. Right? So subtract 0.275 times 137.5 over 2. And I got 68.75 for the value of the moment there. And then what? Well, we're going to subtract more moment off. That's what this negative area says. But it's just going to move down linearly. and hopefully we'll come to 0. Let's find out. What is this area? Well, it's a half times 137 and a half. So 137 and a half times a half is 68.75. So in fact, it does come to 0. Okay? So there's the shear in the moment diagram. Now, where's the beam going to break? Well, let's see. Basically right here is the worst place at 0.225 meters over. Well, plus a half if you want to add it. So 0.725 meters from the end. That's where the moment's the highest. What about shear? Well, shear is actually highest out at this end. But again, shear usually doesn't cause failure in the beam. Questions? Doing okay? I hope this review is helpful. You guys seem to be able to keep up with me, and I'm glad for that. That's a good thing. Because this is the very basic stuff you have to do in order to calculate the stresses in the beam. And that's really what we're interested in.